Hello mathematicians, let's have a look at global maxima and minima. And these are not that difficult, and we've alluded to them in earlier questions. So what we have on the right here is a graph of a cubic function, which we can see has a maximum and a minimum, but we've restricted it to a certain domain, which is 0 less than or equal to x less than or equal to 7. So the graph doesn't exist, as far as we're concerned, outside this domain. So what we notice is that we've got turning points, but they are local maxima or minima, because the maximum just here is not the biggest y value on the graph. The minimum here is the biggest y value, but it's referred to as a local minimum, and they may also be the global maxima or minima. In the case of the maximum value, it's definitely not, because we can see this is the maximum value of the curve over this domain. But in the case of the minimum, then it is the same. So we have a minimum point which is both the global and the local minimum, and we have a maximum point which is the local maximum, but it's not the global maximum. So when we're going to determine maximum or minimum values over a domain, we need a sketch. And obviously what we need to pay particular attention to will be the turning points, we know how to find those, and the value of the function at either extreme of the domain. So here we have an example. So in this example, we're going to sketch this particular function, which is a nasty looking function, and then we're going to find the absolute minimum and maximum values over this particular domain. So finding the absolute maximum and minimum values is going to involve us finding turning points from our sketch and also looking at what happens at the ends of the domain. But sketching the function is the key to this. So if we look at our function here, in our curve sketching menu, we did things like, or we looked at things like having an idea of the domain. So if we look at this function here, the one we're sketching, then we can see that we are not allowed to have x values which are going to make x squared minus 1 less than 0. In other words, the domain is restricted to where x squared minus 1 is greater than 0. It can't be greater than or equal to 0 because we're not allowed to have 0 on the bottom, so it's got to be greater than 0. So if we think about that, what we can see is that our values of x must be less than minus 1 or greater than plus 1. We can also see that we are not allowed to have, if they're less than minus 1, that means that they've got to be lower than this asymptote or further to the left, and greater than plus 1, they've got to be further to the right than this. But our domain was restricted between minus 2 and less than or equal to plus 1, but we're not even allowed to equal plus 1. So the only part of the curve we need to draw is the part to the left of minus 1. So what does that curve look like? Well, we can do a few calculations. We can get the first differential. So our first differential using the quotient rule, put down the bottom and square it up the top, multiply it by the differential of the top, which is 0, put down the top, which is 1, multiply it by the differential of the bottom, so you might need to be careful with that. So then our first differential is this expression here. Now, if we want a turning point, then we need the numerator to be 0, in other words x to be 0, but we're not allowed to have x equal to 0, because we have to have values of x which are less than minus 1. So in the part of the graph that we're plotting, there is no turning point. So if we look at the edge of the domain, when x equals minus 2, y is 1 on root 3, so it is a particular value. And as x tends towards minus 1 from the positive side, from the negative side, so as we put values of x in here which are a little bit further to the left than -1, we're going to get y tending to plus infinity. So over our required domain, the absolute minimum is going to be at 1/√3, and the maximum is actually plus infinity because the curve goes off to infinity.